As we're moving through this unit and we're talking about these line integrals of conservative fields and our shortcut rule, kind of using the fundamental theorem of line integrals, we have two big questions that should be arising. Question one, how do we know whether or not a given vector field F is conservative? As well as our second question, if that vector field is in fact conservative, how do we find the potential function of F such that we have the conservative vector field equal to the greater? And I know these are burning questions for you guys. Don't worry, we have a component test for conservative fields. And what this component test for conservative fields says that if we have a vector field and it's on an open, simply connected domain, and the component functions have continuous first partial derivatives, then the vector field is conservative if and only if we have this situation where I can create all of these three equivalent partial derivative matchup equations. So for example, we have p, partial of p with respect to y and x are showing up in there. We have n, partial of n, both with respect to z and respect to x. And then m, partial of m with respect to z and partial of m with respect to y. Let's look at an example or two of determining whether or not a field is conservative. Here we're given a vector field, e to the x cosine y I minus e to the x sine y j plus zk. And we're asked, is the field conservative? So in order for us to do this, we're going to take the partial of m both with respect to y and z, the partial of n with respect to x and z, and the partial of p with respect to x and y. So we have the partial of m with respect to y and z. M with respect to y equals negative e to the x sine y, and m with respect to z equals 0. N with respect to x is negative e to the x sine y, and n with respect to z is 0. P with respect to x is 0. P with respect to y is also 0. Py and nz, py is equal to nz, so that is one part. Mz equals px, as you can see there, and n partial with respect to x equals m partial with respect to y. So we have to show that these three equations are true, and if these three equations are true, then we can say that the vector field is conservative. Now I used a shorthand partial derivative notation compared to what we have up here, but they do have to match up. Partial with respect to y needs to match partial of n with respect to z. M with respect to z needs to match p with respect to x, and n with respect to x equals m with respect to y. I think if you are thinking about setting this up, you can organize it like this and it will always work out that way, kind of like a loop, the way I see it at least. P to n, n to m, m back over here to that p value. And when I was taking the partials, this was my first, or in a sense, x term, and I took the partial with respect to y and z. I had my second, or we could say like y term. I took that partial with respect to x and z. And then my third one here, this was my z term, and I took the partial with respect to x and y. So I hope that helps you to kind of visualize. In two variables, it's less confusing. Let's look at one of those examples real quick. If we were dealing with f just in terms of I and j being a two variable function, x and y, we just need to show that m with respect to y equals n with respect to x. So for example, we are given f of xy, our vector force field is 2xy cubed I plus the quantity 1 plus 3x squared y squared j. So taking the partial of this first term, m with respect to y, that means we treat 2x like a coefficient, which gives me 3y squared, or 6xy squared. Then looking at n with respect to x, looking at this second term, n with respect to x, the derivative of that constant 1 will be 0, and the derivative of y squared will be a constant, so that will stay. 3x squared becomes 6x, and then we have our y squared. And since these two are equal, then yes, it is conservative. So here we have talked about in this video, if we want to show a vector field is conservative, as we know that conservativity, being conservative, is pretty important to simplifying our line integrals, then this is how we check, either with two variables, or we have our definition here for a function in terms of x, y, and z. So that's it for this video. In the next video, we will take functions that we know are conservative, and then we will find their potential function.